accept the idea of weight being indicated by the tension in a string, then there is a very interesting consequence of that. I have here a pin which is completely frictionless, and I have on both sides a string, and this string has negligibly small mass. Let's just assume that it is massless. And there is here an object M1, and there is here an object M2, and I'm telling you that M2 is larger than M1. So we all know what's going to happen. The system is going to accelerate in this direction. M2 will be accelerated down, and M1 will be accelerated up. What comes now is important, that you grasp that. I claim that the tension on the left side must be the same as the tension in this string on the right side. T left must be T right. Why is that? It is because the pin is frictionless, and it is because the string is massless. Take a little section of the string here, a teeny little section. If there is a tension on it, there is a force in this direction, and there is a force in this direction, these two could never be different, because then this massless string would get an infinite acceleration. So there can never be a change in tension from this side of the string to the other. If you take a little section of the string here, there it is, teeny weeny little section. So there is tension on the string, and there is tension on the string. This one could never be larger than that, because this little piece of string would get an infinite acceleration. So because there is no friction on the pin, and because the strings are massless, only because of that must the tension be everywhere the same. If there is friction in the pin, which we will do later, then it's not the case. Given the fact that the tension left and the tension right are the same, I must now conclude that these two objects have the same weight. Because didn't we agree that tension is an indication of weight? So these objects have now the same weight, and some people may say, oh, that's a lot of nonsense, you must be kidding, if M2 is larger than M1, this must have a larger weight than that. Well, they are confusing weight with mass. It is true that M2 is a larger mass than M1, but it's equally true that the weight of these two objects is now the same according to my definition of weight. Let us calculate the acceleration of this system, and let's calculate the tension. And let's see what comes out. I first isolate here object number 1. So this is my object number 1. I have gravity, m1g, and I have a tension T. Non-negotiable. T be better larger than m1g, otherwise it would never be accelerated up. And we know it will be accelerated up. So what do we get? We get T, I will call this plus direction by the way, minus m1g equals m times a. So the tension equals m1 times a plus g. Hey, we've seen that one before. This one is being accelerated upwards. Notice it gains weight. That's the tension. And this is the acceleration. I have one equation with two unknowns. So I can't solve it yet. But there is another one. There is number 2 here. For number 2, we have a force, m2g, and we have the tension up. This one better be larger than that one, otherwise it wouldn't be accelerated down. Let me call this direction plus. The reason why I now switch directions and call this plus as well as this is a good reason for it. It's not so arbitrary anymore. I know that this acceleration is going to be a positive number because it's going in this direction, it's a given. If I called this negative, I would get here a negative acceleration for the same thing for which I get here a positive. That's a pain in the neck. I don't want to have a plus and a minus sign there, have to think about that it means the same thing. So the moment that I define this the plus direction, I know that this acceleration will also come out to be the same sign as this one. So I flip the signs there. So now I apply Newton's law. I get m2g minus t equals m2a. And so I get t, I write it here, equals m2 times g minus a. Two equations with two unknowns. Well, that shouldn't be so hard to solve these two equations. You can immediately eliminate t, by the way. If you add this one with this one, you already, I call this equation 1, and you call this equation 2. You immediately lose your t, and you get that the acceleration a equals m2 minus m1 divided by m1 plus m2 times g. And you substitute that a in that equation, and you'll find that the tension equals 2mg divided by m1 plus m2. This is very easy for you to verify. Let us look, this is m1, m2. 2m1, m2, I lost 1m, 2m1, m2. Let's look at these equations. Let's scrutinize them a little. Let's get some feeling for it, rather than accepting them as being dumb equations. Let's first take the case that m2 equals m1, and I'll call that m. Notice that a becomes 0, and notice if you substitute for m1 and m2 m here, that you get 2m, you get mg. So t becomes mg. That is utterly obvious. If m1 and m2 are the same, nothing is going to happen. They're going to sit there, the acceleration will be 0, and the tension on both sides, which is always the same, we argue that, is going to be mg. Clear. Now we're going to make it more interesting. Suppose we make m2 much, much larger than m1, and in a limiting case, we even go with m1 to 0. Let's do that. What you see now, if m1 goes to 0, this goes away, this goes away, a goes to g, and t goes to 0. If m1 is 0, t goes to 0. That is obvious, because if I make m1 0, m2 goes into free fall. And if m2 goes into free fall, its weight is 0, and so the tension is 0, and that's exactly what you see. And you see that the acceleration of that object is g, which it better be, because it's in free fall. So you see, this makes sense. This is exactly consistent with your intuition. And if you wanted to make m1 much, much larger than m2, and you take the limiting case for m2 goes to 0, you'll find again that a goes to g, and that t goes to 0, except that now the acceleration is not this way, but now the acceleration is this way, and now this object will go into free fall. And therefore there is no tension in the string anymore. m1, if I return to the case which we have there, that m2 is larger than m1, m1 is being accelerated upwards. That's non-negotiable. So it must have gained weight. m2 is being accelerated down. So it must have lost weight. It's just like being in an elevator. There's no difference. They each weigh the same. One loses weight, the other gains weight. They each weigh the same. And so I can make the prediction that if this is m2g, which was its original weight, and this now is the new weight, t, that m2g must be larger than t. m1 gains weight, so t must be larger than m1g. m2 loses weight, so t must be smaller than m2g. That's my prediction. It has to be. And I can show you that with some easy numbers. Let m1 be 1.1 kilograms, and let m2 be 1.25 kilograms. Frictionless system, and the string has a negligible mass. What is the acceleration A of the system? I get m2 minus m1, that is 0.15, divided by the sum, which is 2.35, and that is approximately 0.064 g. approximately 0.064 g. It's about 1/16 of the gravitational acceleration. So it's a very modest acceleration. What is the tension? Well, I substitute my numbers for m1 and m2 in there. You can take for g 10 if you like that. And you will find that the tension equals 1.17 g. And now, look at what I predicted. They both weigh 1.17 g. That's non-negotiable. That is my definition of weight. The tension in both sides is the same. That's my definition of weight. This is their weight. This one had a weight 1.25 g without being accelerated. You see, it has lost weight because it accelerated down. This one had a weight of 1.1 g. You see, it has gained weight because it's accelerated up. So you see, the whole picture ties together very neatly, and it's important that you look at it that way.